Swayam Prabha. Digital India. Educated India.
Lead lag dynamics, because here last time I mentioned to you the hinge offset and the spring, they give the effect of stiffness, and normally the rotating lag frequency square is k zeta over I b omega square plus you can have it m x c g over okay, which is essentially, if you have uniform mass, this will become three over 2 E bar over L bar, where L bar is, you know, that is 1 minus E bar. Usually the choice of the lead lag frequency is in the range of articulated blade, it will be around 0.25 to 0.3, because there won't be any spring in the case of articulated blade, only hinge offset. Only hinge offset, it is always articulated rotors. You can have that E bar is of the order of 0.04, something like that, around that range, okay, 0.4, yeah, 0.4, 0.6. So if you have this much, you can divide only this term will not be there, because there is no spring. So only this term, and your frequency will be 0.25 in the operating non-dimensional, like flap is 1.09, this is 0.25 to 0.3. But if you put a spring, which is equivalent for a hingeless blade, because you have a restoring spring effect because of the hingeless blade, there is no hinge, then the frequency is kept at it goes to 0.7. You try to design to have it around that. Now you may ask, can I have more than one? Yes, for some configurations the omega bar RL, that is the non-dimensional lead lag natural frequency, is more than 1, and some it is less than 1, more than 1, less than 1. The definition that goes is, if it is less than 1, it is called soft in plane, it is a name. If it is more than 1, it is called stiff in plane. Okay. Now which is better? What is the effect of this frequency on the overall vehicle or the blade? Because right now we have treated only isolated lead lag motion. When you combine with flap, you are going to have flap lag motion. In addition, the fuselage can also start moving, because fuselage has some motion. That means the coupling of lag with respect to flap motion or with respect to fuselage motion, they can lead to instabilities. Okay. Isolated lag is fine, that means just pure lag motion, it is stable, because the damping is, of course, purely aerodynamic damping in this case, We have not put any external damper there. Okay. It is only drag force. In the case of flap motion, it is a lift force that provides the damping. In the case of lag, it is only the drag, and the drag is very small, okay, compared to the lift. That is why the aerodynamic force in the lag motion, the drag is very small. Because of the damping is very small, but by alone it will not go unstable. When you couple with flap for some combination of frequencies, that is all, it is not that always, some combination of frequencies, the blade will go unstable. That is the aeroelastic instability, flap lag instability, which is something unique for rotor blades. You do not face that kind of an instability in the fixed wing, because you have this bending and this bending, that is all. Whereas in fixed wing you do not have this bending, only you take torsion and bending, out of plane bending. Here two bending motions can make the blade unstable. Okay. Now, for you to analyze, then you have to solve coupled flap lag aeroelastic problem. I will not go into the details of that. Usually, if you take a stiff in plane rotor blade, stiff in plane means that lead lag frequency is greater than 1. You keep it around 1.5 or 1.4. Okay. Then technically you can avoid, the flap lag instability, but you have to keep it far away. But if you are not keeping it far away, then those rotors, that is stiff in plane rotors, are prone to flap lag instability. But if you keep it around 1.1, 1.2, then it will go unstable. So, earlier people did that, I will show later that diagram. But stiff in plane blade, if you keep the frequency far away, no problem, it will not go unstable. Now, then why we can always have every rotor blade as a stiff in plane rotor blade? But the problem will be, it will have a lot of vibratory loads. Okay. So, you can avoid that by keeping the frequency away, but then your vibratory loads will be high. Then the other question is, okay, can I bring it lower than 1, that is soft in plane. Soft in plane blade anyway, because you are keeping the frequency far away from near the flap. Flap is around 1.09, so do not go near that frequency. Then soft in plane blade, you can avoid flap lag instability, but you will have another type of problem, which is the ground resonance. I do not know who all came that day for that presentation. That is a ground resonance, in which blade lead lag motion coupled with the body motion, and then that will go, it will be very catastrophic actually, and you have to avoid that. But the loads are less, vibratory loads. So, the question is, what kind of rotor system you will choose for your helicopter. If it is usually two bladed rotors, please note that two bladed, they are normally stiff in plane. Okay, they are normally stiff in plane, and keep the frequency away, and you do not get into ground resonance problem, which is fine. But the loads will be high. On the other hand, if you go to soft in plane, yes, but you have a problem of ground resonance. But for you to solve that problem, you have to develop coupled fuselage lag dynamics. That is the dominant thing, coupling. That is pitch or roll motion of the helicopter will couple with the lead lag motion, and then the whole helicopter will go unstable. That is called ground resonance. It is even before it takes off from the ground, but you also have air resonance. Okay. So, these are the problems. Now, you want less load. If you say vibratory load, okay, go for soft in plane blades for main rotors. Okay. Main rotors of the helicopters design soft in plane, but then they get into ground resonance. So, what you do is you put a damper. So, dampers are put on the main rotor for the lead lag motion. Please understand, the damper is only for lead lag. There will be either a hydraulic damper or sometimes elastomeric damper, which is more sophisticated. You can put a damper. That means physically you have to attach, and they have to check the damping level, oil level, or how good is that. Okay. But for tail rotor, usually you go to stiff in plane, but then keep the frequency away from the flap lag instability zone, and you do not have to put a damper. That is why this is a very normal question I ask the defense people. You always have a damper for the main rotor, why you do not have a damper, why put it off, why you do not have a damper for the tail rotor system. Okay. Tail rotor systems, by design you try to have it stiff in plane and then keep the frequency away, but make sure that that frequency is far away, and then you do not have a damper, absolutely no problem, but loads will be high, but that you live with it, because tail rotor loads are not very high, so it is okay. So, you see, in the design of and the selection of rotors, the frequency placement plays a major role, and depending on where you place, then you have to add additional system, because the system can go unstable. So, you say, okay, I have to put one more damper. So, the flap lag instability is one more critical problem, and that critical problem comes where you keep this. Okay. Rotor fuselage problem is another critical problem, that again depends on where this frequency is. So, it is not that when you study helicopters, you get introduced to these individual blade motion and their dynamics, but that is not the final analysis or design, because this is just to give you some glimpse of, okay, what is the lag dynamics, what is flap dynamics, next we will do what is torsion dynamics, each one independently, but no rotor operates in independent mode, okay, and they all are coupled. Now, analyzing flap is very, very important. Here there is not much analysis, I do not do any analysis, I will just say only the frequency, because if you want to analyze, then you have to analyze this motion along with either flap or fuselage motion, then only you will bring out some new phenomena. Therefore, you will find that the amount of material that is devoted to only lag dynamics is very little. Some books do not even talk about that. If you look at Patfield book, he will never mention in his whole book lag dynamics. It is all flight dynamics only. But flight dynamics, he will only look at flap motion. So, it is like what is important for a particular dynamics, you use it, but of course, everything is part of it. But if you want to get a good understanding of the physics of the problem, do not try to put everything and then you have no clue. So, you split the problem. That is how we say, okay, lag, let me look at it, how the blade will move, flap alone. Next we go to torsion, because the critical thing in lag is these two, I would say the two soft in plane, stiff in plane, you may call it phrases or something like that. No, ground, because you have the stiffness of the landing gear play a role. The moment you lift off, the ground is gone. Okay. Then it is a different dynamics, because that is why sometimes you lift it up, but see you okay. This may be, now this is supported, landing gear support. On the ground, this can be modeled by this spring and damper. That means this can pitch and roll. Okay. The physics is different in each case, and which ground it is standing, that also matters, whether it is a concrete ground or whether it is soft ground or it is ice or grass, because what happens is the stiffness changes. So, usually whenever they make helipad, you see they make a concrete, but you can't have concrete everywhere, but for normal operation you put it, but then when you want to test it, you go and land on ice. So, you have to take the helicopter there, and what is the stiffness of the ice along with this stiffness, okay. And they have done go to Himalayas, make a ice pack and then make the helicopter land and then do the test, make sure that everything is fine, then you come. If it is, yeah, no, rotor and fuselage, where, what is the damper? No, that damper has no use. See, that damper, there is no damper, they do not put a damper, do not think that they put a damper between rotor and fuselage. Now, where did you, huh? No. You have an isolation system, please understand, between the rotor shaft to fuselage, you have an isolation system, that is to reduce transfer of vibration to the fuselage. This instability is not related to that. This instability, what happens is this can move, you say pitch roll. Rotor, I am just showing, the rotor blade can bend like this, okay. When it bends, I am just drawing for two bladed. The CG of the system is here, and that keeps, when it rotates it churns, that means that is giving a imbalance or unbalanced mass which is going around, and that combines with the fuselage motion and it will start heavily oscillating, and it is very catastrophic, because the moment the blade touches the ground, the blade is gone. It's a teetering, what they do is they make it stiff in plane. See, this happens at a particular combination of frequency matching, okay. So, you have it as a stiff in plane range. If you draw the diagram of actually how the frequencies go, the frequency of that full dynamic system, not just a lead lag alone, please understand. But it is there is something more into that, because one is a non-rotating frame, another one is a rotating frame, okay. Now, each blade will be rotating. So, you have to have each blade equations, then they are getting affected by fuselage motion. So, usually there is something called a transformation that is done from rotating frame to non-rotating frame. That transformation is called the multi-blade coordinate transformation. Okay, there is a mathematical transformation, then get it into fixed frame mode. In the fixed frame, physics is okay, CG is moving, that is all, but you have to know at what rotor RPM, operating RPM that really hits it, and then you avoid that. Okay. So, but your rotor RPM always starts from 0 to 100%. Definitely you may cross the resonance point, you may cross the resonance point, or if you want you shift it up. Best is you put a damper. Now there are two types of thing. One, you can put a damper right on fuselage, that is in the landing gear, because some of the helicopters have skid landing gear. That is why you have to be very careful whether skid has its own characteristic. You go to wheel type is some shock absorber and other things, that will have a different characteristic. Helicopter may be same. Actually ALH, yes, they had one version which is the skid, another version which has this wheel type. The wheel type, yes, they had initially some problems, and then they have to put a damper, increase the damping here, tire pressure, everything is matches. It should be very, very critical. So, the analysis you do, finally make sure that during your operational range you do not get into ground resonance problem, and one of the ways to avoid is put dampers. Okay. And damper you put, but again please understand, damper you simply say okay, put a damper, then its weight, cost, maintenance, everything gets added, and that becomes a very critical component. It is not that it is a non-critical. Okay. That is why if you want to know the importance of lag motion, I would put it, the importance of lead lag dynamics of the blade is not in isolated lag dynamics, it is actually in combination with other modes, the importance has come out. So, these are problems people have solved, I will show a few things. So, here only the basic thing is what is soft in plane, what is stiff in plane, that is all. Yeah. Yeah. Soft in plane usually may lead to having a damper, you cannot avoid having a damper. No, flap lag instability usually soft in plane, you see the frequency, these two are soft in plane because they are below 1, and hingeless blade you do not go beyond 0.7, do not go near 1. If you go near 1 you will get into flap lag instability. Please understand, it is not that what I am saying is, when you take the lead lag frequency in the vicinity of flap frequency, you will have a resonance problem. But vicinity means how close, are you going to go to 1.09 or no, even if it is 1.3 you may get in, 1.2 you may get, 0.9 you may get, but that will happen at a higher degree of pitch angle sometimes, then you may not operate at that pitch angle. So, you will say okay, but if you are 0.7 you will not get into that instability.
And on the tail rotor we like to have a stiff in plane.
Yep.
But then we are not much bothered for the loads which are going to come.
Yeah, you say whatever load you will take it.
That's what
Yes.
because the amount of load is less.
The basic load itself is less, vibratory load, so you say it is all right. Otherwise you have to put a damper there.
Make it soft.
If you want to make it soft in plane, then you may land up with some other problem. But even stiff in plane, please understand, it is not you make it 1.2.
Then you have to place it far.
You have to place it far. If you make it 1.2, you are going to have instability. That instability is flap lag instability. Okay. So, usually flap lag instability as a, I will just show a diagram. It is usually, I think this is which is flap, which is lag. I think this is, I think omega lag, I think. think this one minute, I'll just check that, because I don't want to make a wrong diagram. This is just for your, okay. Here the instability zone, it will be drawn very crude approximation. This is the rotor flap frequency, rotating flap natural frequency, rotating lag natural frequency, and there will be some kind of a curves like this, something like these are each one corresponding some pitch angle theta 0 collective. Okay. The curves will be, this is like a bubble, this is called a bubble diagram, name itself is bubble. What happens is you operate at different collective angles. Of course, you have to have aerodynamics. Please understand, this is a aeroelastic instability diagram. I will go into the detail later when I will see whether we will go into that, because if you have a large pitch angle and any combination of frequency within this, in this bubble, any combination of, here this is around 1.0 and it starts from 1.0 and goes, okay. Here it is 1.0 lead lag. If you have a point here, suppose if this is say some 0.3 radian, theta naught 0.3, which is about 15 degrees. If I keep the blade at 15 degrees and operate it, any point here inside is unstable, in the sense any combination of flap lag frequency which lies within this zone, the blade will go unstable. Okay. Suppose I am not operating at 15 degrees, I operate at 0.2, that is 10 degrees. Okay. Then this bubble will come. That means if you are outside this bubble, for less pitch angle you are stable. Okay. Like that you have small bubble zone, but normally in the rotor blade you will know what angle you will operate, and this diagram is drawn. This is a standard famous diagram. Okay. And this, of course, lock number, all those things will come. You can draw several curves of this type, and what not people will say is, hey, let me go, you know, omega flap is around 1.09 or something, you know this point, you can't take it too far unless you introduce that what is that, flap pitch coupling. You can go straight, go in the lag mode, either you are here, okay, which is a soft in plane below 1, or take it very far, so that you are not going to hit this bubble region. Okay. But soft in plane you avoid flap lag instability if you are far away, but you get into ground resonance, but the loads are less. Stiff in plane, far away you avoid flap lag instability, but you have a high vibratory load. Mm-hmm.
So there is no much scope of weight reduction in the structure if we choose soft and plain tail rotor with this gap.
Weight reduction,
If we choose soft and plain tail rotor, so there is not much scope.
see, load means the sense not the mean load, vibratory load. You may put a damper then in that case, because your tail boom with the lead lag can get into, yeah, you will get into that instability, okay, because that is like a ground resonance. The support structure, that is what happened in the tilt rotor, what he was showing that day, the amount of problem they see, he showed that day, but tilt rotor program, for your information, it is wound up, okay, it was shelved just 2 years back, okay. They had this problem because the rotor is rotating, the wing can vibrate, it gets into all sorts of instability problems. Of course, it took 50 years, what he said is true, 1950 they started the whole project, okay. So, the weight point of view, I don't want to get into whether this rotor is, in the rotor I don't think you save tremendously a lot of weight, okay. And the tail rotor, of course, I don't know, maybe few kgs you may save, few kgs, that is all. Instead of 1.5 or 6 which you have kept, maybe okay, I will bring it down a little bit, fine. Make sure that you are away from the bubble and your pitch angle is never going to hit that. See, this bubble will keep on expanding, of course, this is based on very simple calculation, not with stall model and other things. But if you use a more systematic analysis, the bubble may become like this for another pitch angle. But if you know that you are never going to operate at this more angle of attack or pitch angle of the blade, it is fine, okay. Because the question is, this is all done in hover condition, all these calculations. Now, suppose you say I am going to do it on the sideward flight or a climb flight or a descent flight, various types of flight conditions, okay. Usually heavily loaded rotor, please note, heavily loaded rotor, the damping is high normally because the rotor thrust is large, but the lead lag damping you do not know, flap damping is high usually. Lightly loaded rotor, yes, it can get into these problems, okay. So, it is a very tricky thing because these results were generated only for hovering rotors, not descending rotor or a climbing rotor. What will happen? Make sure that you are far away. I do not know. Tail rotor, you don't have any damper, that is sure, right? That is all. That means it has to be stiff in plane, that is all, very simple, because it cannot be a soft in plane. Tail rotor, no, because otherwise unnecessarily you will put one more damper, then its own, its own life, all those other maintenance, every other problem. It is better to avoid as many components as possible, but only problem is you cannot do it. Sometimes you have to put a damper, okay, okay. Now, this much is enough for lead lag motion, isolated lag, but isolated lag is stable. Please note that if I treat only lag dynamics, it will be stable, because there is a little bit of damping that comes from the aerodynamics. Of course, if you want to put a damper, external damper, yes, it will be stable, but the external damper is put in only to avoid this problem, flap lag instability or ground resonance problem, okay. Now, let us take the next case, which is the isolated torsional dynamics, but it is a little interesting, but I will, if you want, I will go through the whole very simple model, please understand, very simple model. The blade is rigid blade, straight, and it has a pitch bearing, and you have a control rod, because that is the one which moves up and down to give a pitch angle change. You assume blade is rigid, that means it is not torsionally soft, first assumption you make, okay. And this control system stiffness Kc with the offset A, because there is a linear spring here, there is a linear spring. If you have a hinge, then you know that this into this distance is the angle, okay, because if you take in terms of angle, that will be control into A square, that offset. Then you can have bearing torsional stiffness, you can add, I have put everything into equivalent control stiffness. Now, what is my dynamics? There is a spring, blade is rigid, but it is a two bearing. Bearings are like it is free to rotate, but the restoring force is given by the spring. When it rotates, suppose you keep it at a pitch angle. In this case, you do not treat the blade as a line, you have to treat the blade as a 3D body. Okay. This lateral distribution, for just a simplicity case, I will show. If this is the blade, I am drawing like this. I put one heavy mass here and a heavy mass here, okay. Just it is spinning. Then this is my axis, right. This mass will get a centrifugal force in some particular peculiar direction. That direction is given here. See, this is the center. This mass is offset from the axis. So, it will get a force like this in the inclined direction, okay. And if it is up also, it will get in some other direction. You follow, because this dynamics is a little bit tricky to understand. That is why if you formulate systematically, you will see, okay, what is my moment. Then a component of the centrifugal force will act like this, okay. Because if it is horizontal, this force will go, that force will go, a component will be like this. If you tilt it up, you will get a component in the horizontal, they will try to give a moment, okay. It will add to the stiffness of the dynamics. Now, how do you develop the equations? I will just start that point so that you will know, because this is a little bit complex and there is a very interesting things. That is why there is a word which is called the tennis racket effect. Later I will, because tennis racket is big and he is holding it here and he keeps it at an angle. When he serves, see, if you keep it, if you rotate it, it will try to straighten, okay, because of the two centrifugal force. They will try to come, and when he hits the ball, you will not know which location he is hitting. In the sense, when he is swinging, it may turn a little bit, but then where it hits, you do not know. Initially, you may think it is coming, it may come a little away. So, this is a terminology they use as a tennis racket effect, okay. I will just give the derivation, and this is the reason why you will see control system stiffness plays a major role in when the blade is operating. See, we did the, I gave you the test data, okay. Test data for I think 5 degrees or 6 degrees, 6 degrees 900 RPM you are matching. When the RPM went up, you find that the value you need to have, pitch angle with 6 degree you are getting 60 Newton or 61 Newton, but what was observed was only 52 or 53 Newton. But why that big difference? Okay. You will see slowly that may be due to this reason. Okay. I will just because this derivation I will just show, because this is slightly interesting part, because you take a position vector of any point which is x I, because why I said x I is from the center you go to any line x I, and then in the cross section you have given a pitch angle theta naught, and there is a elastic twist. Elastic twist is because of the deformation of the spring. Okay, so I have added a phi. Theta naught is what was originally set, that is theta naught depends on where your that position is. Okay, and then there is a torsional spring. So you take any point on the cross section, which is, this is your eta, this is your xi, and this is your y, and this is your z, and this angle theta naught plus phi. So take any point on the cross section and write the position vector. Position vector will be x I is along the x direction, then you will have y is, this is j and this is k direction. Okay. And this point is eta xi, that is this point. I am keeping the cross sectional coordinate system. Okay. You will have plus eta cosine theta naught plus phi minus xi sine theta naught plus phi, this is j, and then plus eta sine, it is just a simple coordinate transformation, plus xi cosine theta naught plus phi k. Okay. Now this is my position vector in the rotating frame of any point P in the cross section, any point P. This is the position vector of any point on the blade. Now you have to find out the velocity, acceleration, and then put the expression, inertial load. Okay, I will write the expression for the acceleration of the point P, because this is a rotating frame. What are constants are eta, x, xi, theta naught. Variable is phi. Phi can vary. So you differentiate, you do everything, because find out the acceleration, that final expression will be like this. Okay, minus 2 omega, because you will have, please note this, you can, your dynamics should be good, then you will be able to, you can try. Okay, cosine theta naught plus phi, phi dot minus x omega square I, then plus, I think you can close this bracket. Okay, minus eta sine theta naught plus phi, phi double dot minus eta cosine theta naught plus phi, phi dot square minus xi cosine theta naught plus phi, phi double dot, then minus, sorry, plus xi sine theta naught plus phi dot square, then minus omega square eta cosine theta naught plus phi plus omega square xi sine theta naught plus phi. This entire term is j, okay. Then you add k, eta cosine theta naught plus phi double dot minus eta sine, because you can try this, because when phi dot square, that is why phi double dot minus eta cosine theta naught plus phi dot square, this is k. Okay, this is the acceleration of the any mass point on the cross section. Now you want to write the equation of motion. So inertia moment, you write inertia moment is as a vector is integral volume r cross p cross rho okay. Rho is the mass per unit length, sorry unit volume, I am sorry, this is the mass per unit volume. Now what you do is you take this cross product, okay, I am not going to write all the things. You will have ijk components. What we need is, because we are interested in only the torsional motion, that means the inertia moment only about the x axis is what we need, okay. Because after that you take the cross product, then simplify, you get the inertia moment about only the x axis, that I will write here, and you will get cross sectional integrals, okay. You will get the m phi along x, that is the inertia, m phi I, or no, why I put phi, m I only along x axis, okay. And I am going to do this volume integral. What I will do is I will split one along length, another one cross sectional area, okay. Now cross sectional area, the rho dA I will write separately, because for the entire cross section only thing variable is eta and xi, theta naught phi they do not change, okay. So you do the cross sectional integral separately, and then when you do it you will have 0 to L, this is the length of the blade, minus I m, this is the symbol I am using, I will tell you what is this, eta phi double dot minus omega square I m eta sine theta naught plus phi cosine theta naught plus phi, this is the product. Then minus omega square I m eta psi cosine square theta naught plus phi minus sine square theta naught plus phi, okay, into dx. Now where this I m psi is area rho eta square dA, and then I m eta is rho psi square dA. This is the area, and then this is the cross product. I m eta psi is rho eta psi dA. Okay, these are the cross products. Now you see this psi is eta square. Please understand. Don't. This is like your area inertia. This is now mass moment of inertia per unit length. That's all. Now this is my inertia moment, and I have to get aerodynamic moment, and then effect of the spring moment. When I add all of them, that is my equation of motion. So inertia moment, I got this mi plus m aerodynamic moment, and then spring moment due to the control system or all the combination, the torsional spring. You put all of them equal to 0, that is your torsional equation. But please understand, I am having everything in cosine theta naught plus v, sin theta naught plus v. This is not a very simple equation. Okay. So what is done is, yes, this is about the, because I have put that pitch axis. Now my mass can be anywhere, mass center can be anywhere. Mass center, see, that comes in the, in this. Where is the mass center? In the inertia itself it will come. This is about the x axis, because this is the feathering axis. Where is the, this is the acceleration at the particular point. See, this is the, what is it? Moment is force. This is force per unit volume, r cross f. Okay, that is the inertia moment. That's all. Okay. Now what you can do is you can combine this aerodynamic moment and, but aerodynamic moment, when you say it is a oscillating aerofoil, because the phi is not constant, it is a time varying, because phi is a function of time. That means you are talking about moment on the aerofoil which is a function of time. Okay. So it immediately goes to unsteady aerodynamics. When you talk about lead lag, I never expressed any aerodynamic term for lead lag motion also. You are having the blade moving like this, the flow is coming. That means it is a pulsating flow. You want the drag force in a pulsating flow. Okay. We do not have expressions for those things. Later we will make a lot of approximation, and that is why we will say, okay, this is the aerodynamic load. That is why I did not put any aerodynamic expression when I derived my lead lag motion. Flap, yes, we use the quasi steady. Here again, if you want, you use the same thing. Torsion also you can use again quasi steady motion. So this is where your complexities start appearing from the aerodynamic model. Now I will just write the equation of motion, and if I, now I have to assume, because this is an integral over L, my cross section properties can vary along the span, because they need not be constant. Okay. Now I have to make an assumption that I am having these properties are constant along the span, then it becomes easy for my integration. Okay. So I assume that the properties are constant, and my equation becomes minus L. L is the length of the blade, right from the root to tip you can take it. I m psi psi plus I m eta eta phi double dot minus L omega square I m psi psi minus I m eta eta sin theta naught plus phi cosine theta naught plus phi minus L omega square same I m eta psi cosine square theta naught plus phi minus sin square theta naught plus phi. Then you put a aerodynamic load m a, and because this other load will be k phi into phi equals 0. This is my equation, because this is the moment due to spring. Inertia moment, this moment, but you will now, if you want, you can take all the inertia and spring on one side, keep the aerodynamics on one side. Yeah, maybe I will. No, I don't think yeah, you can remove this bracket itself, not the moment. That's all. Huh? Rho earlier, that includes, that is why I do not take it separately, because acceleration at a point, what I wrote the big expression, it has everything, Coriolis term, but omega is constant. So, there is a, you know that when you take a rotating beam, you will write the acceleration as 4 components: relative acceleration, Coriolis acceleration, angular acceleration, centripetal acceleration. That is for ease of things, but if you read this derivation follows everything, okay. Because if you want to be systematic, it is better to start from scratch, so that your fundamental principles are clear: position vector, then velocity, then absolute acceleration of a point which is in a blade which is rotating, then you will not make any mistake, okay. Now, if you derive that, this is my equation, it will be sin, and suppose if you say my cross section is symmetric, okay, symmetric cross section, then this term drops out, because I m eta psi, this will go to 0, okay. Even if you make this go to 0, this is nonlinear sine. So, what you do is you expand, you do not say my theta naught, suppose you say I am operating at 0 pitch angle, then theta naught also is gone, then my motion is very small, about phi is small, then this term you set it 1, you will have sin phi is phi, okay. Then you will have phi double dot, there is a phi, there is a phi term. So, you have, I have my equations, very simplified, you follow. That means, you are making theta naught equal to 0, phi is small. Please understand, if you make, do not make this assumption, then you have to retain this, then you expand this by sin theta naught cosine phi plus cosine theta naught sin phi, then phi is small, you put that, not that theta naught is small, okay, phi is small, then you keep it. But if you make a very gross assumption theta naught is 0, phi is small, then your equation will become L, because this is just to give you the frequency, but the precise one is L, okay. Then my plus, I am changing the sign, plus L omega square I m psi minus I m eta eta plus k phi p equals aerodynamic moment. Okay. I have made it highly simplified with this assumption. Okay. And I said I m eta psi is 0. So, I make all those assumptions. It is a symmetric aerofoil, theta naught is 0, p is small. Now, you know that this equation you can find out what is the natural frequency. The frequency of this will be omega bar rotating torsion square. This is if this is dimensional, non-dimensional you will get L omega square, okay, because this will be second derivative. So, this is d by dt, so d omega will come. So, you put a non-dimensional, then L omega square will cancel out. You will have I m minus I m eta eta over I m plus I m plus k phi over I m psi psi plus I m eta eta L omega square. Okay. Location of feathering axis 25%, that is all. No, in rotor blade now you see they do not want to keep the CG away from the elastic axis, feathering axis. Feathering axis is, if you keep the feathering axis separately, aerodynamic center separately, mass center separately, then you will have lot of coupling, flap, pitch coupling, everything will come. Okay, because when you flap up, then inertia force will be somewhere else, that will give a twisting. So, you do not want to do that. And if aerodynamics is ahead of the feathering axis, it may twist, lift will twist the pitch angle. You can have some kind of a divergence type of problem which is there in the fixed wing, you will start having. So, here the blade is designed such that mass center 25% card, elastic axis at 25%, but exactly 25, no, if it comes to 24.5, 8, 9, it is okay, take it. Yes, 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 elastic axis of the cross section is also at 25%. This is where the design goes very, very several iterations. The box beam is kept only in the near, trailing edge does not contribute anything. Okay. So, if you really want to know the design of a rotor blade, you can spend your life 25 years, 30 years, then you will be an expert in how to design a rotor blade. Changing an aerofoil, you may change the shape, but then the distribution of the structure and the mass you have to do. So, it is not that simple that I will go and then change as I want. Okay. Now, you see this is my rotating torsional frequency. Usually this quantity, this, because eta, if you look at the eta thickness is related to psi. So, this is usually small, this is a small quantity, okay, compared to this. But do not think that all these are for rotor blade, they are of the order of 10 power minus 3, minus 4, something like that. Okay. Now, if you say this quantity is small than this, that is you write I m psi psi is much smaller than, much smaller, I am just making an assumption, I m eta eta, this becomes 1, okay, 1 plus k phi over I m L omega square. Okay. Oh, sorry. Yeah, I am sorry about that. Okay. Now, you see this particular one comes because of effect. This is due to purely torsional spring. If you have a non-rotating